One of the pillars of a green future is electric power. So by 2030, many thousands of specialists and managers are needed in the battery sector in Europe. To prepare us for this task, we created a place to train these experts, our ELLB. Here, we empower battery experts with leading-edge knowledge to shape Europe's green future. ELLB, European Learning Lab Battery Cells, part of the Fraunhofer Research Institution for Battery Cell Production FFB.
Hello everyone, and a warm welcome to our third live battery webinar presented by the European Learning Lab Battery Cells as a part of the Fraunhofer Research Institution for Battery Cell Production FFB. My name is Phillip Suttmeyer. I'm the project manager for the academy activities at the Fraunhofer FFB, and I have today's honor to guide us to the following lecture. In November 2022, we already got some first insights in the European battery ecosystem and an overview of the main battery markets, key players, and the cost drivers in the battery cell production. In our second webinar, a few weeks later, we also got an overview about material cycle of lithium-ion batteries. Today, we are going one step further and we are taking a short journey through the sustainable battery cell production and the digital twin. But before we start with our speaker presentations, I would like to give you, and especially those guests who missed the last lectures, a small overview over the Fraunhofer FFB and the European Learning Lab Battery Cells, ELLB. Also, I would like to present the webinar's program and today's speaker. The Fraunhofer FFB is located in Münster. It is an open battery cell factory for research and development purposes, which claims to become the center of development of a modern and scalable battery cell production for Germany and Europe. This claim is also fixed in our value proposition called Innovations for an Efficient and Sustainable Battery Cell Production. To ensure that the production in Germany can provide new battery technologies more efficiently, more cheaply, and in the highest quality in the future, the federal government and the state of North Rhine-Westphalia are founding the Research Factory for Battery Production with a total of 680 million euros. The factory will provide infrastructure for small and medium-sized companies, but also large companies and research institutions can test, implement, and optimize the near-series production of new batteries with a theoretical yearly production capacity of up to 7 gigawatt-hours for electrode material. In addition to those technical supports for the upscaling of battery cell productions in Europe, a further aim of the Fraunhofer FFB is a transfer of battery knowledge to close future skill gaps. This is why the European Learning Lab Battery Cells was established. The demand of the ELLB is to empower battery professionals with leading-edge knowledge to shape Europe's green future. The responsible project team for this task unites the competence of 5 different Fraunhofer institutes, the Fraunhofer Academy, and also the Fraunhofer Alliance Battery, and ensures that everyone will find the right course and lots of knowledge on the subject of batteries. The targeted philosophy is characterized by the following claims. We focus a close cooperation with relevant European players. The development of our curriculum will be marked by the iterative exchange with industry partners and also with an agile approach to address changes in the market and quickly create added value. We will include our industrial production lines, for example through augmented reality applications, and offer virtually interconnected smart learning. We will also add innovative possibilities in training and curriculum and also innovative learning environments based on the new work principle. Our first program on the market is a webinar series which provides a short overview over these 4 topics. As already mentioned, we started with an overview about the European battery ecosystem. For all of you who missed this webinar session, there are good news. You can find the recording on our website. The second webinar had its focus on the material cycle of lithium-ion batteries, the challenges that come along in the process of production, and an overview of recycling and its changes. The recording is also published on our website and on our YouTube channel. In today's third webinar, Sustainable Battery Cell Production and Digital Twin, we will discuss sustainability issues in the classical lithium-ion battery cell production, as well as the use of the digital twin. Last but not least, the forecast of the battery value chain regards the political, strategic, economic, and social challenges arise in the future when establishing the battery value chain. This webinar is dated for 27th of March 2023. All these topics can be intensified by our following program, the pre-charger workshops, which will deepen the topics in practical seminars present in Münster. This program starts in end of April 2023 and is open for registration on our website. Feel welcome to visit and check out our homepage and courses for more information and further booking options. For today, our focus will be on our third webinar. Our three experts, Dr. Guinevere Giffin from the Fraunhofer Institute for Silicate Research, and also Daniel Reichert and Julian Grimm from the Fraunhofer Institute for Manufacturing, Engineering and Automation, took a deep dive into the sustainability of lithium-ion batteries and had a look on the possibilities of the digital twin and its key questions for us. In the next hour, we will learn about the manufacturing of lithium-ion batteries and its factors about sustainability along its whole value chain. Further, we will have a close look on the chances the digitalization brings to the manufacturing of lithium-ion batteries. And in conclusion, we are dealing with the digital twin and its cases in the battery cell production. Afterwards, if you are interested, you are very welcome to join us for another 30 minutes for question and answer with our experts and enter the discussion. If you like to address questions in the ongoing presentation, you can use the chat function in Teams. All questions will be saved and answered at least in the following Q&A. I wish you all a good time and hope you will enjoy today's webinar. I'm now passing on to Gwen, Daniel, and Julian. Thank you for your attention, and now let's start the session.
Hi, everyone. And thanks a lot, Philip, for the introduction. I hope you can all see my screen. So, also hello and welcome from my side. In the next few minutes, I will guide you through the lithium-ion battery production process. So, before we start with the production process, I'll give you a brief summary of the parts we need to get for a working battery. We need the so-called active parts, which are essential for the energy storage and charge transfer processes like the anode, cathode, and electrolyte. And then we also need the passive parts like the separator, additives, and the housing of the cell. Let's take a look at the manufacturing process by getting an overview. The process can be divided into the three main steps: the electrode production, cell assembly, and last the cell finishing. Within the first block, the electrode production, the battery or its starting materials go through the following value-adding steps, which are identical for cathode and anode production. First, the starting materials are pulverized and mixed with other additives to form an electrode paste. This paste is then used to coat the battery cell's current collectors, aluminum and copper foil, and is then dried. After the drying process, the electrode is calendared and cut to the correct size and contacted. Now the electrodes are ready for the cell assembly, the second block of the battery cell production. Here, the layering or winding of the electrodes take place together with the electrically insulating separator. After that, the wound or stacked battery cell is housed in the cell case and filled with electrolyte. The last block is cell finishing, where an initial cycling of the battery sets it up for use. So now let's take a closer look at a battery production process. I will focus here on the most relevant production steps of each of the three presented blocks. The first block, the electrode production, contains of the process step mixing, coating, drying, calendering, slitting, and vacuum drying. Here I will now focus on the mixing and coating process steps. At least two separate starting materials are combined to form a slurry using a rotating tool. In addition to the active materials, the production of the slurry also requires conductive additives, solvents, and binders. Altogether, this final mixture is then called the slurry. The onward transport to the coating process steps take place through pipelines or in atmospherical sealed storage facilities. The carrier film is coated with the slurry using an application tool, e.g. a slop nozzle, for example. The film is then coated either continuously or intermittently, and after this, the coated substrate foil then passes through a drying jammer. So after the electrodes are now coated, dried, and cut to the right size, we can assemble the cell. The cell assembly is where the individual cell parts come together to make the complete cell. Here we have the process steps of winding, insertion, and electrolyte filling, where we here focus on the first and last of these three steps. To produce a cylindrical cell or a prismatic cell, a winding process is carried out. In the production of the so-called jelly roll, the two electrodes and two separator sheets are placed one on top of the other and wrapped around the core. Electrolyte filling takes place after the electrode stack or the jelly roll has been placed in the packaging. During the electrolyte filling, a distinction must be made between the filling and the wetting sub-processes. Because during the wetting, a dynamic under-pressure profile is applied to the cell during and after the filling process. This activates the capillary activities, and the cavities of the porous cell components are filled with electrolyte. After electrolyte filling, the opening of the cell packaging is closed, and we now have a full stacked and closed cell. So now we have a closer look at the last step, the cell finishing, with our now filled with electrolyte and closed cell. This block contains the sub-process of degassing, capping, wrinkling, formation, and aging. Formation refers to the initial charging and discharging process of the battery cell. During formation, lithium ions are deposited in the graphite structure of the anode. In this process, the solid electrolyte interface, which is the boundary layer between the electrolyte and the electrode, is formed. The parameters like current and voltage during the formation vary depending on the cell manufacturer and have a great impact on the cell performance. The formation depends on the cell concept as well as the cell chemistry and represents the core know-how of a cell manufacturer. Aging represents the final step of a cell production and has the goal of identifying cell internal short circuits. The cell properties are monitored by regular open circuit voltage measurements over a certain period of time, up to 3 weeks. So now that we have an idea of what it takes to manufacture a single battery cell, let's take a look at a larger scale, namely the battery cell factory. So what dimensions are we talking about here? Battery factories in the order of an annual production capacity of 1 to 200 gigawatt hours are currently planned, announced, and built in Europe. Investment costs are therefore in the order of 50 million euros per installed gigawatt hour of production capacity. So this is a very investment-intensive industry. And the annual energy demand is not small either, with about 60 kilowatt hours of energy input per kilowatt hour of energy storage capacity produced. So yeah, if you produce batteries with a storage capacity of 1 gigawatt hour, you have an energy input of about 60 gigawatt hour. If you produce 200 gigawatt hour of battery capacity, multiply that by 200. Let's take a look inside the factory and the space requirements of the 3 different production blocks: electrode production, cell assembly, and cell finishing. As you can see, electrode production is the production step with the largest space demand, directly followed by the cell assembly. If we now look one level deeper into the production process, we see that in addition to the actual cell production, shown in light blue here, the drying process and the drying rooms take up a lot of space. These are shown in red here. This huge space demand of this process step is due to the slow drying process times, which, if not sufficiently dimensioned, represents a bottleneck in the battery cell production. So let's take a look at the energy consumption of the individual production steps. First, let me explain the graphic on the right side. This shows the energy input for each production steps per amount of energy storage produced. You can see that the coating and drying and the clean rooms contribute by far the most of the energy demand. The electrode dryers use large amounts of electrical energy to create a temperature profile across the drying production line. Energy consumption in formation and aging is highly dependent on the protocol selected, including number of full charges and length and type of temperature aging. Dry room energy consumption is not directly linked to cell production throughput. The dry rooms are maintaining dry conditions regardless of the throughput of the equipment contained within the room. So optimization of the space in the rooms and therefore volume of air to be dried is critical to ensuring energy efficiency. And last but not least, let's put these findings in the perspective of the European battery production plans. We see huge announcements for new and planned battery factories in Europe. The forecasts and announcement add up to more than 600 gigawatt hours annual production capacity for the year 2025. And by 2030, the capacity is expected to increase by a factor of almost 3 from the planned capacity of 2025. In combination with the knowledge from the last slide that for 1 kilowatt hour of energy storage produced, approximately 60 kilowatt hours of energy input are required in production. This results in an energy demand of over 100 terawatt hours with the forecast ramp up of production capacities by 2030. Or in other words, we need the electricity of over 14 standard nuclear plants for European battery production, so quite a lot. With this in mind, Gwen will later on give you an idea how the sustainable battery production of tomorrow might look like and what saving potentials we have. But before I pass the microphone, I would like to invite you to participate in the short opinion poll here in Teams and express your opinion on the competitiveness of the European battery industry. The initial situation is as follows. The Asian battery industry is traditionally strong, and in Europe, more than 1,000 gigawatt hours lithium-ion battery production capacity are currently announced. Which of the following opinions do you think is the most likely as a reaction to the Inflation Reduction Act of the United States? The number of installed production capacity in Europe will be much lower than the announcement. Second, parts of the production capacity will be realized outside of Europe. Third, the EU successfully initiates countermeasures and most of the announced production capacity will be built. Or last, the announcements will be realized without countermeasures. Please click the most fitting answer in your opinion. I see already 30 answers, very nice, 39. So we have a very strong bias leaning to the second answer. So most of you think that parts of the production capacity will be realized outside of Europe. So meaning that there is a strong influence by the Inflation Reduction Act of the USA. Very little of you think that the EU is successfully initiating countermeasures, and almost no one thinks that the planned capacities will be realized without countermeasures. So roughly 80% go for the first and second answer, so indicating the already strong competition will be probably even stronger with the measures taken in the USA. So thank you very much for participating, and now I hand the microphone to Gwen.
Thanks, Daniel. So in this section, we're going to talk about the sustainability in lithium-ion battery manufacturing. So there we go. So the energy demand and savings potential that Daniel already started to talk about on the previous slide, we're going to look at here in a little more detail. So as Daniel previously mentioned, the largest energy consuming areas are in terms of electrode drying, formation, and aging. So the dry formation and aging, and the dry rooms used to contain the low humidity environments. So in general, the largest contributor for the battery cell manufacturing is the energy consumption. And here it would be interesting, as has been proposed by an agency in the UK, that the energy consumed to produce 1 kilowatt hour of finished cells, so this parameter could be implemented as a core KPI in order to really achieve sustainable cell manufacturing. So if you look at the graph on the right, and think of the different types of technologies, some of which we're going to discuss in the coming slides. So things like alternative drying methods, changing of formation protocols, the use of microenvironments, and so on. Through two deployment, technology deployment levels could in fact lead to about a 65% reduction in energy consumption. So let's look at a few of these in particular. So electrode production is one of the most energy and cost demanding aspects. So the state of the art, as Daniel mentioned above, is the deposition of a slurry on a substrate, so on the current collector, followed by a long drying step. So this implies that you actually have to have very long ovens. You need about 1 meter of oven for a production speed of about 1 meter per minute. So if you look at the graph on the right, this is a small pilot facility that is part of the Fraunhofer FFB. And here you can see they have about 8 meters of drying space. This is the blue section or greenish blue section in the middle. However, in an industrial scale drying facility, you're really looking at about 80 to 100 meters of drying. And so therefore, this is 10 times as long, but would enable a production speed of somewhere to 80 to 100 meters per minute. So you can imagine the energy consumption for this is extremely high because you need the air supply for the drying, the exhaust, and of course you need the explosion protection and solvent recovery units due to the use of NMP as a solvent for the cathode production. And so therefore, there's a number of ways that could be used in the future to make electrode production greener. So for example, you could avoid or replace the toxic and harmful materials by switching to, for example, an aqueous processing for electrodes. Less demanding processes in terms of solvent or alternative production technologies such as printing could be used. Or the third alternative is a dry coating process could be used. So this could be things like extrusion, the solid application, or printing or spray coating, all of which would come under the topic of dry coating. So what I'm going to do now is I'm basically going to go through each of at least a couple of these options. So in terms of aqueous processing, the big advantage is you eliminate the need for NMP or basically you would substitute NMP with water as a solvent. This also avoids the use of a fluorinated binder. So in terms of materials cost, this would be replaced by something like carboxymethyl cellulose or with, for example, SBR, which is a latex type binder. Of course, other binder systems would be possible. And therefore, by moving to water, you don't need the solvent recovery system. And an aqueous process is already an industrial standard for anodes. However, on the cathode side, there are specific challenges associated with the active material itself, which make this challenging. So, for example, degradation of the cathode active material can occur. So things like the leaching of metals and the subsequent deposition of surface impurities. So in particular, lithium leaching is an issue. And this is generally worse when you have a higher nickel content in the active material itself. This results in a rapid increase of the pH and the current collector corrosion. However, here you have to sort of look advantages and disadvantages. And one aspect that may actually help in terms of realizing aqueous processing is this could also enable water-based recycling processes. So here you might see sort of the recycling aspect influencing in the future the production processes through what's called design for recycling. In terms of dry processing, in general, you have a procedure where you take a dry mixture of the powders containing the active materials, the binders, and the conductive agents, and then you mix those together and follow that with a direct application either on the current collector and then through a calendaring step, or you form basically freestanding electrode films. Here, it's easy to control the electrode thickness and the density. The benefits from a dry coating process would certainly be the reduced environmental impact. So you need lower energy demands because you no longer have to remove solvents. Here again, you would be able to avoid things like the use of NMP, and there's a cost reduction in terms of both capital and operational costs. So there's basically three methods that you can use. The first is the Maxwell type process. This was typically used for supercapacitors and has been taken over by Tesla for some of their production processes. It basically involves the powder dosage into a calendar, and then this is formed into a freestanding film that is subsequently pressed onto the current collector, as you can see here in the figure on the right-hand side. A second method would be extrusion. So here you take all of the relevant materials, you put those into a compounder, they're mixed together, and then they come out through an extruder, which allows a direct connection between the powder and the current collector through a second calendaring step, and thus you have then the free or the final electrode. And then finally, the third process is you can do a direct powder application through, for example, a spray coating process where you put that spray directly onto the current collector itself, followed by a possible hot calendaring step. And so in all three of these cases, you would be able to avoid the use of solvents and therefore avoid the need for the drying process. However, you do have to take other steps into consideration, like in this case, the hot calendaring. So now we're going to move into savings in terms of the infrastructure around the production. So here specifically in terms of cleanliness, in terms of dry rooms. So any production area where you're dealing with open cells have specific requirements for the purity that's needed. So for example, the electrode production, the labs would be ISO class 8, and in cell assembly, you're looking at ISO class 6. So to give you an idea of kind of where this compares to other sectors, ISO class 8 would be in the same range as for example, precision technologies or medical technologies. Class 6 would then be moving towards things like the pharma or food industry, but you don't need a level that is as high as, for example, in the semiconductor industry. The need for increased clean rooms basically has a direct influence on the investment cost. So in terms of setting up the clean room in the first place, here you can see on the bottom level, in the bottom of this table, for a given clean room, here we're talking about 15,000 meters squared. Basically, you have about 1.5 times the investment cost when you go from a clean room ISO 8 to a clean room ISO 6. You also have a dramatic increase in terms of the electricity costs, here about a factor of 4 when you increase to ISO class 6. Dryness is also a very important issue in terms of cell production. Generally, the electrode production, so for example, the cathode and the vacuum drying can take place at lower dew points. Why is the dew point here the relevant parameter? Because basically the ratio of the dew point to the actual temperature is what gives you the amount of water in the room. You may be more familiar with the term relative humidity simply from everyday life, weather, things like that. However, relative humidity isn't really appropriate for this level of dryness because you're well below 1%. The cell assembly then needs to take place in much drier environments. So here you're talking in the range -40 to -60, but more on the drier end. And it's important to realize that the investment and the running costs are exponentially dependent on the dew point, or basically on the dryness required. And one thing it's important to note is the use of nickel-rich cathodes materials are increasing the dryness requirements. So here I have 2 exemplary dry rooms. So here a -60 dry room on the left, a -40 dry room on the right. And you can see both in the investment and the running costs that going from -40 to -60 is a huge difference. And effectively, if all of the processes could be done at -40, this would be a savings of about 65%. Now, of course, dryness has a direct impact on the quality of the cells, and therefore there's other solutions that are basically needed to be considered. So first, if we look at the dryness requirement as a whole, the advantage of looking at a -60 system is you have a high production quality. And it's really easy to have results or a point of reference because this is the R&D standard. And when you have this type of a system, it's possible to shift to lower dew points if you need it. On the other side, with a -40 system, you have lower investment and construction costs, lower running costs, and the overall physical footprint is less because you don't need as much periphery to maintain this environment. And therefore, there are new solutions like room-in-room encapsulation that could be considered and are being considered. So for example, you could either use mini or micro environments where basically you take certain aspects of the production and move them into areas of different dryness. So for example, you could put the production area in a -40 dry room and then certain equipment in a mini environment with a -60 dryness. Or you could do 3 different areas. There are, of course, advantages and disadvantages to this as well. The advantage of encapsulation is you typically would have a lower investment and running costs because you have a lower footprint that is at a higher dryness. In addition, you're moving people out of the dry room. The disadvantage is you simply have a lower flexibility. It makes for more difficult handling for the workers themselves. There's less data about this, although these types of micro and mini environments are also becoming more common in the research setting. And you have to keep in mind the equipment that you need for those particular steps have to fit inside the encapsulation area. So there's also fewer equipment manufacturers that are making equipment at the moment, at least, to fit into these small environments. And then the final point I'd like to address today is the potential for energy demand and cost savings in wetting and formation. So as Daniel mentioned above, the wetting and the filling are actually two separate sub-processes, and wetting takes time. The electrolyte has to enter all of the pores, and this is really a bit of a slow process. At the moment, there is not really any good visualization process. It's only possible with extremely specialized equipment. And so inline monitoring of wetting is only really possible with electrochemical methods. So nothing where you can actually see how the wetting is progressing. However, there is work being done in this area. So for example, there's R&D for monitoring method development that would actually give you a visual picture of what the wetting process looks like. On the formation side, the cell finishing is time, space, and capital intensive. And here you have a trade-off between formation speed and so energy and time consumption, and the quality. In addition, you have the aging process that is about 3 weeks. And so here, if you could find ways to either reduce the aging time or get the same quality, but with a faster or lower temperature process, that would also give really good options for further savings. So that's what I would like to share with you today about sustainable production. Before we go to Julian and the digitalization aspects, I'd like to have a sort of a short discussion in terms of we're going to have a word cloud poll. So there are many ways to shift towards green and sustainable battery production. What are the most important aspects, technologies, and drivers for a green and sustainable production? So in a second, there's going to be a field pop up on your screen, and you can just type in an example of something that you think or a particular aspect that is important for you in terms of achieving sustainable production. So I see lots of things here in terms of changing production processes. So things like dry coating, solventless production, looking at the energy sources. There's also a few things coming here in terms of looking at different battery chemistries, specifically green materials. So materials definitely can play a role. What else do we see here? Things like design for recycling or the use of renewable energies as the energy source for production, and along with basically new technologies. So for example, options in terms of sodium-ion production and things like that. Okay, so those are all very good points. One that I do see in the middle is basically the digitalization or the use of digital twins. And on that note, I'm going to pass the microphone and he can take us through the next part.
Hello, everyone from my side. My name is Julian Grimm. I'm working at the Fraunhofer Institute for Manufacturing, Engineering and Automation IPA in Stuttgart at the Center for Digitalized Battery Cell Manufacturing. And as Gwen told before, besides sustainability, digitalization is set to create competitive advantages. And in the next few minutes, I want to give you illustrative examples for digitalization in battery cell manufacturing. First of all, I want to clarify the word digitalization. And in manufacturing, or especially in lead manufacturing, the physical machines are the baselines, the process chain for digitalization. And here we have different stages of digitalization, which are increasing in value. The first level of digitalization is transparency. This means that we have data acquisition and that we have additional sensors and real-time data so that we can get the data out of the machines. The second stage or level of digitalization is the interconnection of systems. And here we want to have an interconnection between the different data which we collected. So we can combine these raw data to new information, or we can also have an interconnection with humans or users, for example, in a user interaction. And the third level of digitalization is the autonomy, which has the highest value. And here we are also combining more data, and we have decision-making, autonomous decision-making. We may have prediction models. And based on this, I want to highlight an example IT infrastructure behind or for the digitalization, at the example of the Center for Digitalized Battery Cell Manufacturing. And here again, manufacturing process is the baseline, so the physical entity, the object which we want to study. And here we want to get the data out of the machines, and for this we have developed the station connector, so equipment adapter, which we can do this based on the different heterogeneous control systems from the machines. And based on this, we can have tracking and tracing of the data from the battery cells. And to combine these services and data from the machines, we need to have an integration middleware. And for this, we have developed the manufacturing service bus. And this manufacturing service bus is connecting the different services. And now we want to have a modular IT infrastructure to have more digitalization services, for example, in experiment management or cell monitoring. And with this modular and expandable IT infrastructure, we are able to develop these different services and then add them into the IT system. After giving you an example of the IoT infrastructure, I want to give some examples for the single stages of digitalization, and I want to start with the stage of transparency. One example for this could be intelligent workpiece carrier, which we have developed to be able to track the parameters of the cells and the process parameters and the machine parameters together with the environmental parameters. And with this workpiece carrier, we are able to track these parameters and combine them with a specific cell. The second example is for the interconnection of systems. And here I brought the example of a digitalized quality management system. And what's happening here is that we have an interconnection of the parameters. And this takes place that we are having process parameters from the manufacturing, from the machines. And we have also intermediate product features which we are gathering, for example, from sensors. And by combining these parameters in a quality model and combine them with real data or with real world data, we gain knowledge on the quality of the cells in the manufacturing process, and thus can tell something about the quality of the battery cells. And the third and last example is for the stage 3 autonomy. And here I brought an example for an adaptive process control. And currently, quality is usually assessed only at the end of the production process. And therefore, possible scrap in the subsequent process steps, they're getting manufactured and getting value creation, but it's already scrap, but we don't know it yet. And thus, we have a lot of scrap at the end, which got some value creation. And the potential here is that with information on the quality in the earlier stages in the manufacturing process, and the information on cause-effect relationships, The idea is that we can adapt process parameters in the following process steps to increase the quality and to reduce scrap overall and to identify scrap in an earlier manufacturing process. And if we're able to have these cause-effect relationships, then we can adapt following process steps and therefore hopefully reduce our scrap. Now, after we have the digitalization, the examples for the digitalization services, I want to give you a short introduction on digital twins or digital twin. And in our understanding, the definition of a digital twin, you can see it here on the left side. And I've highlighted the most important characteristics of a digital twin. So first, it's a dynamic model, so the model parameters update regularly, and we have a real-time data interaction. So we are not using data only from databases, but we have a streamlined data process from the manufacturing process. And advanced system analysis means that we have models and analysis and which go beyond simple statistics. And last but not least, actions, which means that we have in a digital twin, we want to have a feedback to the system so that we are able to control. So we don't want to not only do reporting or monitoring with digital twin. So basically, the difference from a model to digital twin is based on these characteristics. So it's the dynamic model parameters, the real-time data interaction, and the advanced system analysis. If you are now talking about digital twins, what we found is that a digital twin is built up from different building blocks. Here on left bottom side, you can see the equipment machines with the sensors and the control systems, and we want to gather the data via connectors, and we can save them in a database. And here we have a streamline data process, and we have for example, simulation data as well in our databases. And one important part of the digital twin is the model in which we want to make analysis. And on the top, you can see the IT system components which are needed for digital twin. So we need an integration middleware which combines the different services with the different models and connectors that we can connect the data. And we want to have a service. This service can provide different tasks, and the service needs to have a user interface so that the user can have an interface and that we have actions on the physical machines via the control systems. When we are talking about digital twins, we suggest to specify the different maturity levels of it. So we can have preliminary stages to the digital twin, which can be a simulation model where there's no connection between the physical twin and the digital twin. And then we can have a digital shadow, which only gathers data from the physical twin, but it's rather only a reporting or monitoring system. And then we can have a real digital twin with a bilateral data interaction, so we can gather data as well as we can control the system, the physical system. And then, one of the higher maturity levels is the intelligent digital twin. And here we think that we can have a higher degree of autonomy. And further, currently, there are approaches to describe a more mature digital twin, which is said to be cognitive digital twin. Besides the maturity levels, the digital twin can be subdivided by the character of its physical twin. So we can have a product digital twin, we can have a process digital twin, or a digital twin of the machine, and we can also have a digital twin of a building. So basically, we can have a digital twin based on all on different physical systems. And the digital twin technology can also help to connect different lifecycle phases. and thus increase the value of digitalization with the interconnection. And so we can start with the product digital twin in design, and then develop a manufacturing digital twin in the manufacturing phase and combine it with the product digital twin. And yeah, in the usage phase, we can combine the information from the different from the two digital twins and use them in the usage and end of life phase. And now staying in a life cycle perspective, but highlighting some kind of another point is an example from the initiative Catena-X and its connection to the digitalization. On the slide, you can see the way we used to think, so that we are having basically the sourcing and the disposal. And the way we have to think, however, is that we should look more on things like different circular loops, for example, reuse, remanufacturing, or recycling, and thus minimize the disposal. And here, in order to connect the data from the different lifecycle phases, a digitalization service needs to implement it, and this could be the digital battery pass, which Catena-X is also suggesting as a possible solution. And here, the digitalization can help to simplify the battery pass and combine the data from the different lifecycle phases, and thus improve the decision making. So now this is the end of my presentation, and I also want to invite you to participate in the last poll, the evaluation of the battery pass. So the battery pass targets on increasing the transparency for the produced batteries. And on a scale from 1 to 5, how critical do you see the collecting and disclosure of the necessary data along the life cycle of battery? Okay, so it seems that it's yes, almost 4 stars. So it's it has the tendency to be critical. And as a researcher, I have hoped to see the criticality of the data for the battery pass being low. Reason for this is that we have the necessary transformation of our economy and the usefulness of the concept of a digital battery pass for end-of-life treatment of battery, for example, reuse or recycling. I'm very interested in your opinions, and so we can have the discussion afterwards, and tell us all your critical thoughts in the discussion later. Now I want to hand on to Phillip. Thank you.
Oh, perfect. Thank you, Julian. Thank you, Daniel. Thank you, Gwen. Thank you for your interesting presentations and your given insights in the factors of sustainable and digital manufacturing of lithium-ion batteries. And also great thanks to the huge number of interest participants joining us today. Now we reach the end of our lecture, and we will stop the recording. Right after, we start with the casual Q&A with our experts for further discussions and networking. So you have the chance to discuss with our experts and ask your questions. I've seen we have some questions also in the chat. And finally, I would like to leave once again my recommendation to check out our website for all further events and learning opportunities. The registration for the webinar session number 4 and for our pre-charter workshops here in Münster are already opened. Hopefully we will see you again in the next events, and thanks again for your interest, and a good day to all of you. Let's get over to the Q&A.